In this video, I'll work through two examples that show you how you can use logarithms, and in particular the properties we just learned in the previous video, to solve problems. So let's do that. Let's start with the first example. Oh, here it is. So suppose we have an equation like this, some sort of exponential growth, and we want to solve for t. So we want to know what's t. So when there's an exponent upstairs in an equation, you can bring it downstairs by taking the logarithm. And in order to be fair, you need to take the logarithm to both sides of this equation in order to preserve the inequality. Now, before I take the log of both sides, I'm going to simplify this a little bit. It usually makes your life a little bit easier if you simplify before taking the log. So I'll simplify. I'm going to move this 30 over to the other side. I'll divide both sides of this equation by 30. And let's see, let me do this division. Zeros goes away. 9 divided by 3 is 30. So we have 30 equals 1.2 to the t. So now I'm going to take the logarithm of both sides of this equation. So log 30 equals log of 1.2 to the t. And that's, so I should probably put another parentheses in there. So it's log of 1.2 to the t. So then we have this property from the previous video, or from the book, or from your memory, that when you have an exponent, log of a to an exponent, you bring the exponent out front, in front of the log. So that means this becomes log 30 equals t log 1.2. And that means then that we can just solve for t. Remember, we're trying to solve for t here by dividing both sides of the equation by log 1.2. So let's do that. I'll continue over here, I guess. So we've got log 30 over log 1.2 equals t. And at this point, we'd need a calculator to go further. So let's fire up the calculator. So 30 log divided by 1.2 log equals, so this says t is 18.65 approximately. And let's check to see if that's actually true. If true, this says that 1.2 raised to the 18.65 power times 30 should give me at 90, or almost 90. So let's see. So 1.2, working here on my calculator, raised to the 18.65 times 30, this is looking good, is 899.2. So approximately 90. It's not exact, approximately 900. It's not exactly because we rounded this off a little bit. We didn't keep all of the digits. You might want to take a moment just to make sure that when you do this on your calculator, you get the same thing. That sounds like a silly thing to say, but there are ways of, there's some common errors people make when entering logs in on a calculator, and particularly this sort of thing. And it's a little different depending on which type of calculator you have, what order you enter things in. So you might want to just double check to make sure that you're entering logs correctly. Okay, so that's the first example. So here's the second example, and it takes us back to chapter 1.2, where we learned about exponential growth and decay. And the chapter claimed that there are two ways of writing exponential growth or decay. We could write it with an initial value times some a to the t, or we could write it using e as a base and then this funny k there. And I said don't worry too much about this, but I'll show you in a little bit, and that little bit now is now that you can translate from one of these forms to the other and back again, but using logarithms. So these are the exact same function, they're just written a different way. You can almost think of it as taking a sentence in one language, translating it into a sentence in another language. It's an exact translation, exact same thing, just looks a little different. So since e's are involved, we're going to need natural logarithms. And let me just remind you what those are. They're defined in the same way as base 10 logarithms. So e to the natural log x is x, or log of e to the x equals x. So e, it's just this funny number, 2.7818, blah, blah, blah. We'll learn later where that comes from. For now, it's just some funny, weird number that some math people apparently really like. And we can use that instead of 10. And then everything else is the same. So exponentiating and logging, they undo each other. You start with x, you log it, you go, oops, I didn't want to do that. You exponentiate it, and you're back to where you started from. So let me just sort of put this in a circle here. Those are some reminders about what natural logs are. So we want to write this as that. So we want these two things to be equal. So let me write that. We want 50 times 0.8 to the t to equal p naught times e to the k t. So we want this equality to be true. So we can see that p naught is going to be 50. And then we're going to have to worry about this exponent thing. So we see that p naught is 50. And then let's think about this part of the equation. So we need 0.8 to the t to equal e to the k t. But remember, when we have exponents multiplied together, that really kind of means that they're double exponents, right? 10 to the a to the b is 10 to the ab. So I'm going to use that property of exponents, but I'm going to kind of use it backwards. And I'm going to say that this is e to the k to the t. So e to the k to the t is the same thing as e to the kt by this property here. So now I've got something to the t equals something to the t. And so those somethings must be the same. 0.8 must equal e to the k. So let me write that. We're almost there. 0.8 is e to the k. And we want to know what k is. That's the thing we're trying to figure out, p naught and k, so I can write it in this way. So let's take the natural log of both sides. The natural log of 0.8 equals the natural log of e to the k. But wait, e and natural logging, those undo each other. They're inverses of each other. That's what this property is here. So the right-hand side is just k. So we're done. We get to declare victory. So k is the natural log of 0.8. And let's figure out a numerical value for that. So 0.8, and then I hit my natural log button, and hey, I get a negative number, minus 0.223. So k minus 0.223. So this minus here means that we have exponential decay. Here we see that it's exponential decay because the base of the exponent is less than 1. And here it shows up because the number up here would be negative. So let me write this. I guess I'll do this over here. I could say that p of t is 50 times 0.8 to the t. And that's the exact same thing as 50 times e to the minus 0.223t. So these two expressions exactly the same. It's the exact same function, the exact same numbers, the exact same exponential decay. We're just writing them in different ways. So the point of this example is to show you how to go to translate from this form to that form, and you can do a similar thing to go in the other direction. It's a useful thing to know how to do, since both of these ways of writing exponential functions are pretty common, and there are advantages to both. So there'll be a couple homework problems on this week's problem set, so you can practice this.